This is the second of 3 lessons on grid navigation. In this one, we examine the problems of providing a source of grid heading. The modern flight management system is usually polar programmed and can continue to operate in true up to very high latitudes, and, in any case, is not so concerned about chart convergence, as no chart plotting is required in order to provide the required steering signal. However, if grid flying is carried out in an aircraft without FMS, the source of heading is either a gyromagnetic compass or a high-grade gyro. We are going to see how we obtain grid, as opposed to true or magnetic, heading from whichever of these 2 sources we are using. If grid technique is being used because of the problem of meridian convergence at high latitudes, then the aircraft may also be near to one of the Earth's magnetic poles. If so, it may not be practicable to use a magnetic compass because variation may be changing too rapidly, or the horizontal magnetic field strength may be too weak. However, even at high latitudes, this may not always be the case. Flying in parts of northern Canada would probably give a problem. But flying in northern Europe or Russia probably would not, because these areas are a greater distance from the North Magnetic Pole. So it may be possible, under some circumstances, to steer by magnetic compass even when using grid technique. The problem is not too complicated and is very similar to the problem of steering true heading when using a magnetic compass. When using true steering, we apply variation to convert the required true heading to magnetic heading, then apply the deviation to get compass heading to fly. For grid steering, all we have to do is apply a combination of convergence and variation to convert the required grid heading to magnetic heading. Finally, we apply the deviation to get compass heading to fly. Here is just the correction from grid to magnetic. The difference between magnetic and grid heading is called gravation, and it is the algebraic sum of variation and convergence. By using gravation, we can go straight from grid to magnetic. We don't need to bother with true as an intermediary step. By the term algebraic sum, we mean that if the signs of variation and convergence are the same, we add them. If they are different, we take the difference. For instance, a convergence of 10 west and a variation of 5 west gives us a gravation of 15 west. However, if the convergence were 10 west and the variation were 18 east, the gravation is 8 east. Printed grid charts have the gravation pre-calculated by the publisher and printed on the chart. Lines on a chart joining places of equal gravation are called isogrids. For some practice at the relationship between convergence, variation and gravation, look at this situation. A straight line track is drawn between 2 points on a Lambert's or polar stereographic chart. The datum meridian is C. Now complete the attached table. Your first reaction may be, well, how do I even get started? The trick to remember is that the grid track does not change direction. If you have found the grid track at one longitude, it must be the same grid track at all longitudes. Use your mouse to move the numbers below into the correct box. If you're right, they'll stay there. If not, they won't go in. When you're finished, click to continue. Here are the answers. Now let us see how we would use a magnetic compass to steer a true heading as the variation changes, and then we will see that much the same principles can be applied to steering a grid heading. This short triangular navigation exercise, which is typical of a PPL training route, all takes place between 2 isogonals. We use 3 degrees variation for the whole route. However, this route from Norwich to Swansea crosses two isogonals. Assume that we need to fly a mean track of 254 true all the way along the route. We start off with a variation of 2 west. We will need a magnetic track of 256. But as we cross the 2.5 degree isogonal, our variation changes to 3 west. We must now alter heading to give a magnetic track of 257. Similarly, as we cross the 3.5 degree isogonal, the variation becomes 4 west. Another alteration of magnetic track, this time to 258, is required to maintain a track of 254. If a chart is constructed with isogrids, then the same principles can be used to maintain a grid heading when using a magnetic compass. On this chart, the blue graticule is the latitude and longitude. If you use true heading, then here are the variation changeover points. The grey graticule is the grid. If you use grid heading, then here are the gravation changeover points. You can see that the rate at which the isogrids are changing is much the same as the rate at which the isogonals are changing, so it is no more difficult, in many parts of the world, to fly a grid heading using a magnetic compass than it is to fly a true heading. However, one of the reasons that we may be using grid is because the aircraft is at high latitudes. In this case, a magnetic compass may be unusable in some parts of the world because the route is within the 6 microtesla zone and the horizontal component of the Earth's magnetic field is too weak. In other parts, the rate of variation may be changing too rapidly to be usable. In these cases, we would steer by gyro. The errors of a gyro are real drift, also known as random wander, earth rate, and transport wander. Real drift in INS quality gyros is of the order of 1/100th of a degree per hour. However, if an INS were fitted, it would not normally be necessary to use grid, because most inertial navigation systems are polar programmed and can continue to operate in true up to very high latitudes. Nevertheless, if no INS is fitted, on a typical modern airline quality gyromagnetic compass, the gyro drift rate will still only be about 1/10th of a degree per hour when operating in DG mode. In this case, real drift is low enough to be insignificant. Earth rate occurs because the gyro is aligned with true north at some particular meridian. The aircraft then rotates with the Earth along with the meridian, but the gyro continues to remain in alignment with the point in space where it was originally aligned. The correction factor is 15 times the sine of the latitude in degrees per hour. Many modern gyro compasses have a latitude correction control, which is a knob turned by the crew to be set to the local latitude, and the correction is then fed to the gyro. The crew then keep resetting the latitude as it changes. Transport wander is another name for meridian convergence. The gyro is aligned with true north at some particular meridian. Then, as the aircraft travels either east or west, the gyro remains aligned to the original direction in space, but the direction of the meridians, and therefore the local direction of true north, changes. To operate in true, a correction has to be calculated for this meridian convergence. The correction factor is change of longitude times sine mean latitude. However, to operate in grid, no correction is required. What is required is a direction that does not change with change of longitude, in other words, a grid. Therefore, we use the gyro, but without any correction for transport wander or meridian convergence. It is actually easier when using a gyro to fly in grid rather than true because you don't have to correct for transport wander. There is in fact a small error caused by the difference between Earth convergence, which is the gyro correction, and chart convergence, which will depend on the projection and the standard parallels being used. A correction has to be applied, known as residual transport wander. This is fed in either by slewing the gyro or as a false correction to the latitude control, but its use is beyond the scope of this course and is not discussed further. Therefore, to operate with a gyro in grid, all that is needed is to align it to grid north initially, then feed in a correction for earth rate. Real drift will be small with a good gyro, and transport wander will be non-existent, or there may be a small amount of residual transport wander to be corrected. Let's summarize this lesson. It is easy enough to produce a grid by drawing parallel straight lines on a chart. This solves the problem of a constantly changing track direction caused by convergence at high latitudes. However, this solves only half the problem. We still need to convert the heading source, whether compass or pure gyro, to the grid direction. It is perfectly possible to fly by compass even at high latitudes, as long as the aircraft is not too close to the magnetic pole. In this case, we use gravation, which is the difference between magnetic and grid north, instead of variation, which is the difference between magnetic and true north. Gravation is the algebraic sum of convergence and variation. Make sure that you can convert between grid, true and magnetic directions using gravation, convergence and variation, and understand how they are linked. When the compass is unusable because the Earth's magnetic field is too weak or the variation is changing too rapidly, we may choose to steer by gyro. In this case, the three sources of error are real drift, earth rate, and transport wander. Real drift is low in modern gyros and can be regarded as not significant. Earth rate can be mechanically compensated by the use of automatic devices. And transport wander, which is another name for meridian convergence, is eliminated or nearly eliminated by the use of a grid. That completes this second lesson on grid navigation. The next one will look at typical grid exam problems.